Good morning, guys. Here's part 2 of solving trigonometric equations. As I said in the last lecture, we're going to look at using factoring and using identities to solve some more complex type of expressions. We looked at in the last lecture about how to take an angle or take an equation, figure out what angle created that ratio based on whether it be sine, cosine, or tangent, and actually find all the solutions that every place that the sine, cosine, or tangent curve would intersect that y value, whatever it happens to be. So again, we're going to take that and expand it for these more complex types of equations. This is big kid math as we start. The beginnings of big kid math. 2 cosine squared of x plus cosine of x minus 1 equals 0. Now, that looks kind of complicated. Well, I got 2 different kinds of cosine. If it was regular cosine and cosine, I combine them. I have a single cosine. My isolate variable, go through all our fun stuff. But I've got a cosine squared and a cosine. Think back to quadratics. What if I had 2t squared plus t minus 1 equals 0? How would I solve that equation? Well, it's a quadratic. We have lots of techniques. I can do completing the square. I can use quadratic formula. I can just factor it. Or check to see if it'll factor. 2t squared would be 2t and t. Negative 1 would be plus 1 and minus 1. Check it. 1t minus 2t gives us negative 1t. Remember your process. If the number matches, the numbers are fine. If the sign is wrong, change your signs. So I would change this to minus 1 and plus 1. So minus 1t plus 1t, or plus 2t gives us the 1t we need for the middle. It's the same thing because for these quadratic in the trigonometric form, because once it's in this form, 2t minus 1 equals 0 and t plus 1 equals 0, I have a single t in each expression. So if I do the same thing with my cosine equation, recognize it as a quadratic. First term squared, middle term is half the degree of the first term, and then we have a constant. We just break it up. 2 cosine of x, cosine of x. We just saw that it needed to be minus 1 and plus 1. So when I check it, negative cosine plus 2 cosine leaves me the 1 cosine in the middle. Set each factor equal to 0. So 2 cosine of x minus 1 equals 0. Cosine of x plus 1 equals 0. Now we solve. I have 2 small equations here with a cosine x in each of them. We just solve them separately. And your 1, 2 cosine of x equals 1, divide by 2. Cosine of x equals a half. Get your cosine to the other side, either by using calculator or by setting up your triangle. So we get x is equal to, let's see, inverse of cosine. Cosine's adjacent. Adjacent to 1 is the 60-degree angle. So 60 degrees would be, what, pi over 3? Assuming my arithmetic is correct there. So pi over 3 plus 2 pi n, and negative pi over 3 plus 2 pi n. As we talked about in the last lecture, cosine is positive angle, negative angle, both of them plus 2 pi n. Double check that. Yeah, pi over 3. Okay. Draw out the triangle if you need to on that, or just inverse cosine from the calculator, and it'll give you the 60 degrees converted to radians. Cosine of x equals cosine of x plus 1 equals 0. Subtract your 1. So that cosine of x equals negative 1. Get rid of cosine either by inverse cosine on the calculator or answering the question. So when is the width negative 1? That'd be at 180 degrees. So that's pi plus 2 pi n, right? And negative pi plus 2 pi n. You could simplify that by just saying pi plus pi n, but it doesn't make a difference. As I was talking about the last lecture, This way, we just have to remember one type of expression for cosine right there. We don't have to remember it, or two types of expressions, not three different expressions. Wait, nope. Oh, that's right. We're good there. So, cosine of x equals -1. I need to drop my graph here. Unit circle. -1 means we went left 1. So there's my angle. Happens at pi, and then it happens, every rotation of pi. Okay, so it's just the one time plus pi, plus 2 pi n. If you mess up like I just did and you had the negative pi on there, it's going to put you right back there. You're not going to get the wrong answer because things are going to start to repeat. Values will start to repeat, and obviously you're not going to write it more than once. So if you make that error like I just did, it's not the end of the world. The numbers will take care of themselves. Don't stress. Let the numbers do the math for you, do the work for you. You just kind of hang on to the pencil as we go. So I end up with these three solution sets, or these three generic equations. Now let's figure out what the solutions from 0 to 2 pi are, or 0 to 6.28. So we've got x equals pi over 3 plus 2 pi n. We've got negative pi over 3 plus 2 pi n. And we've got pi plus 2 pi n. Well, let's look at a bunch of n's. I'm going to try n equals -1. Like I mentioned in that last example, in the last lecture, I should have started with -1 just on the off chance that something has occurred to cause that to work. Rarely does it work, but sometimes it does. Just depending on what the angles are. So pi over 3 minus 2 pi. Obviously, it's not going to work because I got 1.05 minus 6.28. That's going to be approximately, what, 5.23, -5.23. Doesn't fit in our interval, so it doesn't work. Negative pi over 3 minus 2 pi n. Negative 6.28. We're punching all this in the calculator. Negative 6.28. Negative pi 1.05, so it's negative 7.33. Doesn't work. Pi over 2 minus 2 pi. Well, it's negative pi, so negative 3.14. Again, that one didn't work. So n equals -1 didn't work. Rarely does it work, but check it, because the one time you don't check it, you'll have a solution there that you should have got. All right, so let's try the 0. Well, pi over 3, 1.05, yeah, that one's going to work. Negative pi over 3 is negative 1.05. That's not going to work. Pi, which is 3.14. Okay, that one works. So we got those two solutions. N equals 1. So pi over 3 plus 2 pi. So 6.28, 1.05, 7.33. Okay, too big, won't work. Negative pi over 3 plus 2 pi. So 6.28 minus 1.05 is the 5.23. That one fits. That's in our 0 to 6.28 range. And pi plus 2 pi is 3 pi, which is 9.42, I think. So that one again doesn't work. So we've eliminated these two, because above and below we found don't work. Let's try an n equals 2 for this one. So I don't have to try that one because I've already found one that doesn't work. The one right before it rather didn't work. So negative pi over 3 plus 2 pi times 2. Yeah, 2 pi times 2 is 4 pi. So 12 in a pinch minus 1 in a pinch is going to be approximately 9. Wow, I really can't do math today. 11 in a pinch. So somewhere around 11 something. Okay, which is obviously bigger than 6.28. So that one doesn't work. So all of our solutions for this problem end up being pi over 3, negative pi over 3 plus 2 pi, and pi. So that is all solutions from 0 to 2 pi of this equation. I plug any one of these answers into this equation, and every single one of them will spit out a 0. Okay, so that keep in context what it is that we're looking for. All right, let's go through and work with a couple more of those. Okay, next example we're going to look at sine of x tangent squared of x equals 3 sine of x. A little bit different than the last one we looked at. It doesn't have just one type of trig expression in it. It actually has two types in there. So typically when we see multiple types of variables or variable expressions at least, we think factor, get everything to the same side. So I'm going to subtract my 3 sine x over. These are not like terms. They have factors that are the same, portions that are the same, but they are not have the same variable expressions overall that would allow me to combine coefficients. So I just have sine of x tangent squared of x minus 3 sine of x equals 0. I can't combine them together, so we just leave them as they are. Now, noticing that they do have something in common, we should see what we can factor, and that would be the common factor. What they have that's the same in each expression, and that would be a sine of x. So if I take my sine of x, pull it out of both terms, sine of x is gone, I'm left with tangent squared of x. Sine of x is gone, I'm left with minus 3 equals 0. So now I've got a factored expression, and I can use my zero product property that allows me to set each factor equal to 0. So tangent squared of x minus 3 equals 0, and sine x equals 0. Let me just solve each one separately. Sine is already isolated, so I either inverse with the calculator, or I just intuitively think what angle has no height, because sine is my vertical component, so that would be 0 degrees, or 0 radians. Plus 2 pi n, and then the supplement of that is pi, plus 2 pi n. And I could simplify that by just saying 0 plus pi n. It's the same thing, but either way, it doesn't matter. We'll work with it in this form because this is kind of the context we've been working with. You'll start, as we get through more and more of these, you'll start to see little things like that that can clean up a little bit and simplify down, but it's not the end of the world if you leave it in that form for what we're doing now. Let's take the tangent squared x minus 3. I want to add the 3 over. Okay. I've got tangent squared x equals 3. Can't touch the tangent till I get rid of the square. We get rid of the square by square roots. So tangent of x equals plus or minus square root of 3. So x is equal to opposite square root of 3, adjacent is 1. Let's actually pull it up here. It's now another 2 equations. Tangent of x equals positive square root of 3. Tangent of x equals negative square root of 3. So opposite over adjacent, opposite of square root of 3, which is, so I'm writing at 60 degrees, so pi over 3. So x equals pi over 3 plus pi n. And then opposite is negative square root of 3, so that's going down. So that would be negative 60 degrees. So x equals negative pi over 3 plus pi n. Now, you could have used, instead of using negative pi over 3, I could have used, I just want to bring that again. I could have used 5 pi over 3. That's the quadrant. That's equivalent to that. It's one full rotation in the other direction. I could have even used a quadrant 2 angle. What the calculator gives you on that one, I'm not positive. We'll check it right now. So if I do inverse tangent, inverse tangent of negative square root of 3, negative 60 degrees, negative pi over 3. So calculator, so I thought, defines tangent between negative pi over 2, pi over 2, so it should give us the quadrant for it. But we put that with our solution for sine, which was our solutions for sine, which were x equals pi plus 2 pi n, and x equals 0 plus 2 pi n. So this would be all solutions. Again, there's a little bit of redundancy there, but it'll take care of itself. This is all solutions. We want to find just the ones from 0 to 2 pi. So we just start plugging in n's. So I'm going to try n equals -1. So 0 plus 0 minus 2 pi. That's going to give me -6.28. Obviously, it doesn't work. Okay. Pi minus 2 pi, approximately -3.14. Again, not between 0 and 6.28. It won't work. Pi over 3 minus pi, 3.14 minus 1.05, so that's 2.09. So -2.09. Again, won't work. Negative pi over 3 minus pi, which is going to be about 4.19. Negative 4.19. So again, doesn't work. So n equals -1 didn't work. Like I said, check it just in case it's the one time it does come up, does show up. Try 0. 0 is usually the best starting point. So 0 plus 0 is 0. Pi plus 0 is pi. Pi over 3 plus 0 is pi over 3. Negative pi over 3 plus 0 is negative pi over 3. So that one's 0 to 2 pi. There's 3.14, 1.05. Negative 1.05 won't work because we're only wanting numbers 0 to 2 pi. All right, n equals 1. So 0 plus 2 pi is 6.28. So it's too big. So this equation's finished because I got one above and one below that don't work, or one before, one after. Pi plus 2 pi, which is obviously if you're adding 2 pi on, it's bigger, 9.42, I think. Doesn't work. So that equation's finished. Pi over 3 plus 2 pi, again, 7.33. Doesn't work. That equation's finished. Negative pi over 3 plus 2 pi. It's going to be approximately, we've done this one many times already, 5.18 somewhere, or 5.23, I think. So again, it fits in the 0 to 2 pi. It works. So then we finish off n equals 2. Don't have to try it. Don't have to try it. Don't have to try it because the one before didn't work. Okay. And the one before that. So we've already blocked that one off, blocked that one off, blocked that one off. This is really the only one we're left trying. Negative pi over 3 plus 4 pi n. Uh-oh. That's all. Sorry, plus pi n right there. So it should have been plus pi. So that was actually, this is the 2 pi n, or 2 pi. So this is the 5.23. That one will also work. 3.14 minus 1.05 is 2.09. Okay, so those both work. And we would check it for n equals 3. Yeah, we're not checking these. And we should be able to see that if I add 3 pi, which is 9.42, to minus 1.05, I'm going to get 8 point something. So that one shouldn't work either. So what we end up with is our final solution set is 0, pi, pi over 3, negative pi over 3 plus pi, and negative pi over 3 plus 2 pi. All of these solutions, all these angles plugged into this equation, this left side should, and this right side should give us equivalent values. 2 examples of factoring right there. whether it be factoring a quadratic trinomial or whether it be factoring by common factor. We could do factoring by grouping. We could do factoring sum or difference of cubes. Any type of factoring that we've talked about before, we would have to recognize that format is present and then just go through the process of factoring and then solve your final equation once you've got each factor set equal to 0. Okay, guys, we're going to solve this type of equation using our identities. Now, if we look at it initially, this looks like a quadratic. We have a square, we have a linear, we have a constant. But if you look closer, it's actually a sine squared and a cosine. They're not the same. I can't take sine squared, factor it into sine and sine, and have them recombine to give me cosine. So we've actually got to use another strategy, and what that is using the identities to rewrite that sine squared as something with cosine in it. And that is our Pythagorean identity. Remember, sine squared of x plus cosine squared of x equals 1. So I can say that, or switch that order around. So I can say that sine squared is equal to 1 minus cosine squared. And where that helps me is if I do that substitution and I rewrite this as 2 times 1 minus cosine squared of x minus cosine of x minus 1 equals 0. Okay. Just take the sine squared, substitute 1 minus cosine squared. Now I have something that I can either cancel cosines or get into a form that'll factor. So we go through, clean it up, distribute 2 minus 2 cosine squared x minus cosine x minus 1 equals 0. Continue working through it. 2 minus 1 is 1. So 2 cosine squared x minus cosine of x plus 1 equals 0. That'll now factor. Negative 2 cosine x, and we would need this to be minus 1 plus 1 and plus 1, right? 1 cosine minus 2 cosines gives us a negative cosine. So I get negative 2 cosine x plus 1 equals 0. Set each factor equal to 0. Cosine x plus 1 equals 0. Just go through and do the arithmetic. Move the 1. Set cosine x equals negative 1. Inverse cosine that, or intuitively, where are we going left? So that was going to be pi plus 2 pi n. We only get a horizontal distance of negative 1, that's once. This side, move the 1. So negative 2 cosine x equals negative 1. Move the negative 2, and cosine of x equals a half. In which case, go ahead and write it over here. X is equal to, move my cosine in either inverse cosine or work through it intuitively. Cosine's adjacent. We are adjacent to 1 with a hypotenuse of 2. Adjacent to 1 would be the 60-degree angle. So pi over 3 plus 2 pi n and negative pi over 3 plus 2 pi n, along with the pi plus 2 pi n we already found. So we've got all of our algebra that we did after our substitution. Gives us these 3 general solutions that we just start substituting in. And you're going to notice that you're going to keep getting the same answers again and again and again because we're working off of the same ratios again and again and again. So you may get to the point where you just know what the answers are based on how they're written here. But we'll substitute in the negative 1. So pi over 3 minus 2 pi n, minus 2 pi. At this point, we should know that it's going to give us a negative number. It won't work. Negative pi over 3 minus 2 pi, going to give us a negative number, won't work. Pi minus 2 pi gives us a negative number, won't work. So we don't need to try any more negative ends. Try 0, pi over 3, 1.05 works. Negative pi over 3, negative number, won't work. Pi plus 0, pi, it works. Try it equals 1. Pi over 3 plus 2 pi. Yeah, pi over 3 plus 2 pi. It's already bigger than 2 pi, so it won't work. Negative pi over 3 plus 2 pi. That one does work because it's 2 pi. So 6 minus 1 is about 5.23 we've already found. And pi plus 2 pi, bigger than 2 pi, won't work. N equals 2, don't have to try these two because we've already blocked off the solutions. Negative pi over 3 plus 4 pi, 12 minus 1, again, is too big. So our solution set is pi over 3, negative pi over 3 plus 2 pi, and pi. Now, that's the way we can use identities. And we could use any of our identities. Pythagoreans are usually the most common because it leads back into the factoring. But as you'll see, as we work through the problem sets in class, there are a lot of different types of identities and substitutions we can use. There's even other techniques that we can come up with other than just factoring and just doing substitutions with identities. There are other ways we can get to those substitutions other than the way we're presented originally. So we'll work through the problem sets in class. We'll get to experience a lot more of these equations. But the idea is get it into something that you're familiar with as far as process for solving. And then it's just, you've got your solutions, plug in until no more solutions work out. All right. Thanks for watching these 2 lectures. I know it's a long set, but we got to get through this before spring break. I'll see you in class tomorrow, guys.